All right. Hello. Okay. Good afternoon, everyone. We got a lot of material to get through today, so I'm going to go a little bit faster. We're going to be talking about vehicle charging technology and electric vehicle supply equipment. This is basically all the infrastructure that you need to charge vehicles. This is an area where I do some of my research, so we'll get into some of the sort of interesting questions that folks are thinking about right now with regards to infrastructure. So, yeah, I think that a lot of people, when we think about refueling our cars, there's this analogy with gasoline, right? And so that's kind of what folks are kind of most familiar with. But I would maybe sort of posit that the way in which we think about refueling cars, specifically conventional cars with gas cars, might actually be a little bit different than the way we think about recharging your electric car. And I think that there is probably this closer analogy with like charging your cell phone, right? And so how often, so for those of you guys who drive gas cars, like how often do you fill up your gas tank, right? So think about that. Usually, every couple days, maybe once a week, once every other week, depending on how much you drive, right? But with a phone, so who charges their phone once a day at least? Yeah, so most people, right? Yeah, and so the way that we think about refueling, I think, is going to be much more analogous in that way. Yeah, so kind of quick bit of history. Why do you guys think that EVs didn't really sort of take off in the 1900s, right? So we talked about right earlier that electric vehicles have actually been around for longer than gas cars. And at a certain point, gas cars really sort of took off. And so part of that competition is having to do with the availability of refueling infrastructure. So electric vehicles require electricity, but if we think about kind of our electric power system, right, that is definitely a more sort of modern system than what we're talking about with than with electric vehicles. Really, our modern power system didn't really come about until kind of the 1950s, 1960s, where you had a lot more, coal generation, hydropower, nuclear power plants getting constructed. And so the ability of our infrastructure to be able to keep up with the demand was quite a bit different. So most of the electricity usage back then, these are very sort of small uses. Lanterns, like cleaning equipment, farm equipment, and that total capacity that you see on this plot, right, even by 1930, so in megawatts, 30,000 megawatts, whereas today in the US we're closer to over 1 million megawatts. So the ability to provide that electricity is very different. Yeah, compare that to the sort of modularity and ease of installing stations that could dispense fossil fuels, sort of very different picture. And so even back in the 1900s, the accessibility of this infrastructure was quite a bit higher than with electric vehicles. So let's start off with a quick sort of discussion question. Yeah, for those who are on their own tables, maybe you guys can huddle up with some of the neighboring tables. And yeah, let's chat about thinking about what do you guys think comes first, right? This is the classic chicken or egg problem that people talk about in reference to electric vehicles, right? Should we have more cars or do we need more charging infrastructure first? And then who do we think is responsible for building out like that charging infrastructure? So take a quick second and talk about this, and then we'll see what you guys have to say. All right, let's discuss. Okay, how about table way over there? What do you guys talk about? Mm-hmm.
First, it should be the EV companies to be responsible for building the charging infrastructure because, like Tesla, they have like most of the charging stations in the older houses. They're not public, and later on, they will build more publicly, and the government will handle it.
Yeah. Okay. Great. So you guys say EV adoption first, and then the like car companies should be responsible for putting in that infrastructure. Yeah, sure.
I think, like, in a sense, you get waste if you put in, there are potential for waste if you put in infrastructure before adoption, but you're gonna get less buy-in if there's not infrastructure to support. Like, if you get a car and you know that you're not gonna be able to charge anywhere conveniently, then you're not gonna get an EV. So I think, like, there's probably pretty good prediction models, and like, I'm not saying you should build infrastructure for everyone having a car because it's not going to happen, but you can scale up the infrastructure just a little ahead of the market. And then I think like independent contractors could build it. Like you were saying over there, if you're a car company and you want to get into the charging infrastructure market as well, then you can. Or if you just want to specialize in that charging industry and be an independent contractor in that.
Yeah. Yeah, great. Let me actually do a quick survey of the class. So raise your hand. So I'm going to ask EV first or chargers first. So raise your hand if you think it's EVs first. Okay, and then raise your hand if you think it's chargers first. Okay, we actually have a pretty decently even split. Yeah, and I'm not saying or implying that there is really kind of a right answer to this question. Kind of either way is you have some sort of pros and cons, right? And so if you're talking about pushing out the electric vehicles first and then letting the charging infrastructure follow, you do face this exact issue that was just described of, well, I've got all these EVs, but then maybe they have nowhere to charge, right? Or the fact that there's no chargers is going to prevent the adoption of EVs in the first place because people are like, oh, there's not enough chargers, I'm not going to buy an electric vehicle. Likewise, right, we have a similar problem on the charging infrastructure side where if you build out all the charging infrastructure and no one's using it, then the infrastructure is underutilized. And if you're thinking about this from like a business or financial perspective, it's like, how can I actually make any money if no one's there to actually charge their cars and, you know, use my charging infrastructure? So in those particular cases, you know, one may actually consider the infrastructure to be kind of like a public good. And in examples where we're thinking about this under those sort of lenses, then one of the entities that can actually step in to help get these things out, right, without necessarily worrying about the business portion of it is the government, right? And so the government can maybe step in and build out an initial network of chargers to help support electric vehicle adoption, and then you've got this like cyclical thing of like more EVs, and then you'll have charging infrastructure kind of follow. Yeah, and so we're going to revisit this idea and think how this integrates with a lot of the concepts that we're going to be talking about today. And again, not to point in one direction or the other, but we have seen examples in other technologies where we face similar types of issues. So this particular example is, okay, for cell phones, right, do we set up the networks first or do we get the cell phones out first? And in this particular case, it's the infrastructure that precedes the adoption of the actual technology. And so the subscriptions and population coverage kind of go hand in hand, and so that's kind of what you want in order to be most efficient, but they did establish kind of the network first in this particular example. Doesn't need to be, you know, totally dedicated infrastructure, right? You can use, you can use existing infrastructure and kind of layer it upwards, right? And so if we think about in cell phones, like 3G came out first, then 4G, then 5G, and actually later on, you ended up having some of the phones precede the infrastructure. And so, you know, in the first stages of it, where we had networks that were providing the ability to call, right? That came out before the phones, but then there were actually 4G and 5G phones that came out before those networks were sort of more widespread. So even within a single technology, that can kind of flip-flop. Okay, so let's jump back to basics and let's talk about hardware. And I did want to provide just a little bit of context. So we're going to have an entire lecture on charging behavior next week. But I just wanted to start with this to give folks kind of a sense of, you know, the types of charging that happen. So I think when I started this lecture, the conception is mainly around public charging, right? The idea that like we have gas stations for gas cars and we have electric charging stations for EVs. So we do still have that kind of analogy, but the part that's missing, right, is that you also have charging at home. And in fact, most charging happens at home. So you can see here, 2/3 of all charging is almost exclusively at home charging. And then another like 20% is kind of mostly at or near home charging. And then the people who, you know, will have some amount of charging farther and farther away is much kind of smaller. And that, I think, is fundamentally very different from a gas car, where we're typically not, well, I don't know about you guys, but I don't have a gas station at my house, so. Yeah, in terms of the level of charging, which I believe I've alluded to before in this class, and we're going to talk about in a lot more detail in just a moment, most people are charging level 2, some people level 1, and then a very small number of people use dedicated DC fast charging like near their house, right? But the vast majority is going to be level 1 and level 2. So some nomenclature to start us off with. Yeah, moving back to the hardware. So the actual like handle, right, the piece that plugs into your vehicle, we call this the connector or the plug. You've got the entire sort of, the entire thing that we call a charger, that is generically referred to in this field as electric vehicle supply equipment, so EVSE. Technically speaking, it's not necessarily accurate to call all what we think of as chargers and infrastructure as a charger. In the electrical engineering lingo, actually, remember we talked about how you have this converter inside of the car that changes from AC to DC and DC to AC. That would actually be technically, right, if you were an electrical engineer, they would actually call that portion the charger. And that's where you get a little bit confusing into some of this nomenclature, right? These guys actually are chargers because they also have the converters. But then if you're not going from like AC to AC, if you're not putting DC into the car, that means that the car charger is the thing that formally is changing the phase of the electricity. So anyways, we're gonna play a little fast and loose with the terms here. You know, when I say charger, I'm gonna be referring to the infrastructure. Just know that, yeah, in proper nomenclature, this is gonna be referred to as the EVSE. And then the whole sort of location, we would call this kind of the charging station. All right, so types of charging connectors. So unlike gas cars where we just have one nozzle to go in, actually there's this whole ecosystem of charging connectors that actually continues to evolve, and we'll show how that has kind of changed over time. We can put, right, both AC power into the car and DC power into the car. It's maybe a little bit less clear to see in here, but on the slide, the top part is AC, and then the bottom part is DC, and then you actually have one that can do kind of both. AC would be kind of considered slow charging, whereas DC would be kind of considered fast charging. And we're gonna talk about specifically these different charging standards and connector types in just a moment. Anyone have any questions about any of this? Okay, so connectors. Actually, this one is missing the sort of most basic one, which is the J1772. Okay, let me pass these out real quick. Got a couple examples of these. So this one in blue, this is the Chatamo. Not even on here because this is kind of the antiquated one. It's going to be harder and harder to find that. Over here, the big bulky black one. That's the first one that we see up here, CCS. As you pass this around, you know, you can look at the form factor, see how big they are relative to each other. And the other thing to note is these cables are all cut. So just take a look at the cable configuration here. We're going to talk about this a little bit more in a moment. And notice kind of the difference in thickness of the wires as you pass these guys around. So this small one, I have two of these going around. That's going. These are the J1772, and that's going to be for slow AC charging. Okay, so let's talk about speeds of charging. So, starting off with level 1, I've got actually one more example here. So these are actually the full chargers. I've got one level 1, which I'm going to pull out right now. This comes from the first generation Nissan Leaf. Okay, so this operates, as you guys can all see here, right? This is your standard wall outlet. So I could just take this, go to a plug that in, and then on the other side, I've got the J1772 connector. That's the one that's going around on this side. Exact same thing. And I can plug into my car, and I can just charge right out of a wall outlet. So wall outlets operate at 120 volts, right? And so going back to our analogy about water, right? So voltage is kind of like the water pressure. And then amps is essentially like the amount of water, and then power is essentially like the flow rate of water. So if you have lots of amps, you could have high power, or if you had really high voltage or high pressure, you could pass a lot of that, like you could pass a small amount of water, but then the rate would still be fast since it's at kind of high pressure, right? So level 1, we're talking about 120 volts, 10 to 15 amps. So you're on the order of 1.4 kilowatts, right? So the way that you go from the equation is power is equal to voltage times amps. And to give a more familiar, familiar metric, right? This would be kind of like adding something on the order of like 5 miles of range into your battery per hour. Standard plug type wall outlet, so the wall outlets are known as NEMA 615. And the actual connector is with the J1772, which is the one that's going around, or the J3400. I don't actually have an example of that one, but that's the Tesla plug. Okay? Yes?
So what about like 408, 277? Are you charging that?
Yeah. So, well, you're talking about volts. Yes. That is not like really a standardized voltage that is common in the standards for these, but there are people who champion and really push for kind of adding those as standards. There's actually a guy who used to be at Davis, he's now at the California Energy Commission, who every chance he gets is like, we gotta get 277 and 408 as standards in level 2. And that, that may happen. That would enable faster charging, because you could have an equivalent amount of amps, but higher voltage and get sort of higher AC charging speeds. There's a whole bit about compatibility with vehicles, but that's kind of like a separate question. But yes, I would say 277 and 408 is not like a standard voltage that is easily accessible and can be used with the current standards. Okay, so level 2, AC, we have 208 or 240 volts. and then you can have a whole range of different amperages. Okay, so the second generation of Nissan Leafs, so this is actually the one that I was picking up here before, as I was mentioning, that actually came with your vehicle. And so when you bought your Nissan Leaf first generation, you would get bundled with it this charger. And then in the second generation, they were more generous, and you could get a level 2 charger. Notice, right, the plug is different. This is more like what you would plug your dryer into. This is a higher voltage than our standard wall outlet, which means more pressure essentially. So if you had the same amount of current flowing through at higher pressure, you're getting more power. And actually these are also meant to handle higher amperage. I think this one can do 30 amps. And so you would have something like 30 amps times 208 volts, right? And so that would be something on the order of like 6 kilowatts. But technically, oh, you can just leave it up here. Yeah, technically, these things can go up to 20 kilowatts if you have your amperage high enough. The actual connector, right, for level 2 is the same as for level 1. So you can see this is a J1772, same as in level 1. There is a little difference though. You can see here, if I hold up my two, level 1 versus level 2, the conduit is noticeably thicker, right? And that's meant to be able to handle the higher voltage and higher amperage. Probably the most common format in homes. You can install these in garages, right? You have something more on the order of refueling your vehicle, some 12 to 60 miles per hour. This is much, much slower than gas refueling, right? If you were to actually do the math on how quickly gas refueling adds range, it's something like thousands of miles in an hour, right? Because it only takes you about, 5 minutes to fill up your tank, and then you can go 300 miles, so, multiply that by, 10 to 12. So you're much, much slower. On the other hand, you have access to this at home, and so this idea that, I could only do like 10 to 15 miles in an hour, well, if my car is sitting in my garage and I go to sleep every night for 8 hours, that would be more, that would more than refill the entire range of your vehicle usually, given how much people typically drive on one day. Okay. And then the last one, DC fast charging, DC. We are calling these as kind of these individual categories, but the ranges from DC power can vary quite a bit. Okay, most DC is operating at 400 volts, and then newer generation is more like 800 volts. And then amps can be anywhere from 100 to 500 amps. That varies the power between kind of the, if I was giving this class, 8 or 9 years ago, I would have been telling you guys that, okay, 50 kilowatts is kind of the standard. But nowadays, the standard is more like 100 to 150. And at the high end, we have 350. So here, at 350 kilowatts, you're talking about charging speeds that kind of emulate gas stations. And then otherwise, you're talking about speeds where you're charging up your vehicle, in the span of like 20 minutes to an hour, something like that. Okay, and so this one, these connectors are all the sort of big beefy ones that are going around. CHAdeMO CCS, and then the Tesla J3400. Again, I don't have an example of that one here with me today, but that, as you can see, can do all level 1, level 2, and DC fast. Okay, any questions about this? Yeah. All right. So, yeah, let's go through each of these guys individually. So J1772, that refers to a named standard. So SAE, who's heard of SAE before? Yeah, so Society of Automotive Engineers, they are like an international organization that helps develop engineering standards for all sorts of things, including including vehicle chargers, right? So J1772 is the interface for plugging in an electric vehicle. And it's not just the format, there are other things associated with the standard as well. But SAE J1772 is meant to accommodate both level 1 and level 2 charging. So as you guys take a look at these plugs, if you had looked down into, I guess, the nozzle, right, you see a bunch of these little circles. And so what do those circles kind of represent? So we have the lines that are, the lines where the electricity is actually flowing. So for L1, you only need one line and then the other, so that there's 3 kind of big ones and then 2 small ones. The 2 at the top are really where the electricity is flowing. For level 1, you just have one AC line, and then the other one is acting as a neutral. And then for level 2, these are your 2 AC lines that complete the circuit. The bottom big one is just a ground. And then the 2 small ones that you see here labeled as PP and CP in the white circles, these are known as your proximity pilot and then your control pilot. So the proximity pilot is purely like a safety instrumentation. There is a pin on the receiver end that will touch the proximity pilot first. It'll touch it last as you plug in, and when you unplug, it'll sever the contact first, right? And so unless there's contact being made, it will, or I should say, if there's contact being made, right, it will prevent the vehicle from moving, and it will then be the thing that allows all of the systems to start up, right? And then that's the first part that would get disengaged as you pull the plug out. The CP is the control pilot, and that handles communication between the vehicle and the charger and the charging equipment, essentially. So these are kind of the details on the attributes and standards associated with 1772. This is kind of this repeat of what I was showing in the earlier slide, right? But your max power on level 1 is really kind of, either 1.4 or 1.92, depending on your amperage. At 16 amps, you're getting 1.92 kilowatts. And then on level 2, anywhere between, like, I would actually say 3. I think the lowest you can get is about 3.3 all the way up to about 20. The kind of standard L2 that you see out in the wild, I would say used to be 6 kilowatts. But a lot of home chargers now are operating at slightly higher amps, like 40, 50, even 60 amps. And so that would be more like 9 to 12 kilowatts. So, 50 to 100% faster in more modern day L2 charging. Any questions? Okay. Next one, CCS. CCS Type 1. This stands for Combined Charging System because this is actually an extension of the J1772 connectors. Who's got the CCS connector? Anyone hold it up real quick? Yeah, okay, great. So if you look at the top part of it, it's gonna look the same as the J1772. Why don't you bring it down? So, thank you. Yeah, so if you guys all had a chance to look inside the top here, you'll actually see this top part is identical to the J1772. The AC lines actually are not really functional, and in fact, in some of the chargers, you'll see that it won't have these top two, and that's because all of the electricity is actually flowing through your bottom connectors, which is this bottom two parts with these two bigger holes. Notice the size of these holes, a lot bigger, right? So CCS, we're talking about much higher voltages, right? We're talking about 400 volts, and the current, right, is an order of magnitude higher, right? So we're talking about 100 amps, 200 amps, or more. And so the actual size of the conduit here, as you guys, if you guys had a chance to look inside the back end, they're much, much thicker. And this cable, right, okay, it's cut so you can't, really see the full thing, but if you compare the diameter of this cable, much thicker. And these are, bulkier and harder to move around. So in the bottom connectors, this is our positive and negative leads. These are the parts that actually contact for DC electricity flow. Okay. Otherwise, the other pins are the same, so we still have our ground, but the most important ones are the prox pilot and the control pilot, which are telling the car and the charger that a connection has been made, and then communication can happen between the car and the charger. SAE J3400. Okay, so this used to be called the North American Charging Standard. This is what Tesla uses. And then more recently was updated to have a broader set of standard requirements from SAE, Society of Automotive Engineers. J3400 was formed, I think, like a year and a half ago. This one's pretty interesting. It has two leads that are capable of both AC or DC input current. And so if you wanted to go between, right, so, all of these chargers that have been passed around, right, these are on the end of the charger and you plug into the car. But the Tesla vehicle, if you look into the receiving end, can only receive this kind of connector. So you need adapters to go from CCS1 or 1772 to be able to plug into a Tesla vehicle. And vice versa, right? If I had a non-Tesla vehicle and I wanted to charge at a Tesla station, I would need an adapter for that. And the adapters are not just form factors, right? There are specific things pertaining to the standards and the way that they allow electricity to flow and how communication happens. It's a lot more complicated. You can't just take any old adapter, throw it on just to make the fittings right. Okay, and the last one I'll talk about is, well, in North America, this is called Chatamo. That is the one that was floating around, the blue one right over there. A little bit more complicated. You see there's a lot more pins. And actually here, let me grab it for me real quick. So we do have our two big connectors for the DC electricity flowing, but you'll notice that instead of just a control pilot and a prox pilot, there's a whole bunch of other connectors. And so these elements include, okay, there's the ground, you have SS1, SS2, these are start and stop charging signal sequences. There's a pin that grants permission to connect power, and then there are 2 pins for communication protocol. So CHAdeMO, I would say, is one of the older standards that is now outdated. This came in primarily certain Japanese vehicles, most notably the Nissan Leaf. So both the first and second generation uses CHAdeMO, but the latest, sorry about that. But the latest generation of Leafs, I don't think use CHAdeMO anymore. I haven't checked on that recently. But yeah, those would probably be the most common vehicles to use them. And this is definitely a more antiquated format that is, I would say, being kind of phased out in terms of public infrastructure that actually has these types of chargers. CHAdeMO itself is actually it's not like a bad standard or anything. In fact, it does have more capabilities than our more common CCS1 because CHAdeMO actually allows electricity to go both directions. And so that enables you to do certain things where you're like interacting with the grid. And that's a concept that we'll talk a lot about more later on in this class. So for DC fast chargers, these are like the bigger equipment that you see out in public, right? And the reason why we have this, the reason why the format looks so different for a DC fast charger compared to like a level 2, which just has this, bulky thing over here. With DC fast chargers, right? That's equipment that has, it needs thermal management because the equipment can get hot. It's got to be able to transform the power from the grid in AC into DC, and it's got to be able to handle a lot more current, right? And so the electrical equipment tied to DC fast chargers are a lot more substantial and a lot more expensive. But when we say DC fast charging, again, I just want to emphasize that we call it one thing, but there's a pretty wide spectrum of different types of chargers, right? So these on the left are 50 kilowatt chargers. On the right are 100 kilowatt chargers, right? So twice as fast. And then even faster than that. On the left here, we have, 150 up to 220. So these are Tesla's Gen 3 model. These are gonna charge as fast as 200 kilowatts. Whereas over here on the right-hand side, these are kind of like the flagship Electrify America and Gen 4 Tesla chargers. These are in excess of 300 kilowatts and can even charge at voltages higher than 400. Yeah, so how fast is the charger? It depends. DC fast chargers, we may say, okay, this is, let's say, a 200 kilowatt charger, but it might not always be operating at its full speed. And that could be both having to do with the vehicle, but it could also be having to do with the electrical equipment on site, right? So the idea is let's say you're at a 150 kilowatt charger at a station with 10 other chargers that are all occupied. The electrical equipment at that site may be rated only to handle a certain amount of capacity. And so if you were there just by yourself and no one else is charging, then maybe it would have no problem dispensing all of that electricity. But then if 10 other people are charging all at the same time, they will actually throttle the speed of the charger in order to not overcome the like hosting capacity of the electrical equipment at that site. Why would we not just build out the electrical equipment to be able to handle everything at max power? Well, you could do that, but one, it would probably be cost prohibitive, and two, you'd probably have much longer delays on deploying that equipment to a particular site. So people have looked at this and kind of done the math, in some locations, maybe you're slammed all the time, and so you do want to build out that electrical capacity. But in other locations, the chances that everyone's using every stall at once might be astronomically small, in which case you could actually set up a smaller hosting capacity at that particular site. So the ability of the EVSE to sustain its full charging capacity depends on the infrastructure upstream of it and whether or not the transformer can maintain the electricity demands from all of the vehicles. It also will vary, right? We talked about this before, depending on what the car is actually requesting, right? Because your battery would not be able to take the full high, 200, 300 kilowatt power when it's operating at like 80+% state of charge, right? So remember that graph that we had before that was showing cars will charge slower as the vehicle battery gets more full. Okay, and to throw this into even more confusion, you have different standards in Europe and in China as well. So you have type 2 and CCS type 2 in Europe, and then we have GBT in China. And that's because the electricity system is actually a little bit different in EU. They don't have 110 power like we do here in the US, or 120 volts. Not going to talk too much about those standards. Just know that they are a little bit different. All right, so their CCS and their level 2, if you look into the nozzles, they have 7 connectors as opposed to our 5, and that's because their AC is operating oftentimes in 3-phase. And so these configurations can accommodate that and can do lower DC power flow. But again, we won't worry too much about other parts of the world. Yeah, so maybe I'll throw a quick question to you guys. Should governments mandate kind of a single charging standard, or should we kind of let the markets decide? What do you guys think? Let you guys discuss for a minute or two. Okay, let's reconvene. What do you guys think over there? Yeah, your table.
I think we discussed that like competition is pretty healthy and we want to continue, but I don't think this is necessarily the case for the chargers because if you have like different chargers, let's take like phone charging for example. Like even Apple, they changed the most recent models of iPhone to use the USB-C.
Yep.
So this tells us that even conglomerates like Apple recognize that it's counterproductive to have like a completely different form of charger, and this makes it uneasy for consumers. So I think it's important for all of them to work in an ecosystem together so that they can use like premium like charger and this one, give the consumer like better choices.
Yeah, although in that particular example, I'm not so sure it's Apple seeing the light as opposed to them kind of being forced to see the light, right? But yeah, point taken. Anyone else want to talk about what they think? Should governments mandate a single standard? Yeah.
I mean, we kind of talked about how like it's healthy to have the competition, and I think different than the iPhone, because like I thought of that too. It is at least like bigger markets of like a whole place, so you're not gonna be like probably charging your car in China and in America, so you're not gonna run into as many issues.
Yep.
But I think it could be helpful. For example, we're stuck with the imperial system, which is awesome.
Yeah.
And so it could be helpful if we're all kind of moving in a similar direction, because then like when there's new research or things on that charging, everyone's kind of working towards a similar goal. Is kind of what I think.
Yeah, and that makes a lot of sense. You want like unity in direction. Yeah, so great perspectives. I would say, we have essentially these three standards, right? We have CHAdeMO, CCS, and then NACS, or the J3400, the Tesla standard. And to some degree, right, it is important to have that kind of competition. There are pros and cons to specific standards and what they, how they enable infrastructure to interact with vehicles. And it's important to let kind of companies, explore that space and see, what the sort of benefits of one versus the other are. On the other hand, right, when it comes to infrastructure deployments, now it does become more expensive because you have to have, multiple chargers or multiple connectors for an individual charger if you want to have accessibility, right? And, if you are like a private company, or you are operating a private network, not necessarily a private company, but a network that only offers, let's say, like a Tesla connector, right, that cuts out large portions of the market from access. So you kind of have pros and cons on both sides of these. And so let's look at how that has kind of changed over time, right? And so back in 2022, the landscape looked more like this, where essentially we have, again, the three big ones, CHAdeMO, CCS in the middle, and Tesla. I kind of put all of the automaker brands that kind of correspond to particular standards. This chart may look a little bit skewed, but right, just know that it's not in terms of the total EVs, right? So like Nissan and Kia are big players in the CHAdeMO space, and they, especially in the early years, Nissan was responsible for a very large proportion of the electric vehicle market. That portion has kind of shrunk over time. Similarly, the only one here, Tesla, I originally, back in 2022, had put this text here. Both Nissan and Tesla are maybe moving towards CCS, but that may actually have changed, right? And so what ended up happening, we're going to talk about some of the policy regulation a little bit later. But there was essentially a big push to move towards NACS. I will say, all these details that I'm talking about, about particular connectors and the standards associated with them and the details of all these plugs, right? If at the end of the day, you as consumers, we don't care about these things. We want to take a plug, put it into our car, get electricity, and make sure that it works, right? And so this big kind of debate is, this idea about all the like technical specifications that automakers might be conflicting over, but the convergence to a single standard, which a government might push and support, is really to make life convenient for car buyers and EV users in general, right? If I can now go to any charging station and plug in, I'm going to be a lot happier than having to deal with like different plugs and adapters and all of that. So, actually, there was regulation that pushed out a big network that required actually CCS1, but a bunch of automakers decided to make the jump and switch over to NACS or J3400, which is the Tesla system. And so in 2025, right, so at the start, right, pretty much all of your companies besides Tesla are in CCS1, but then car companies essentially decided we're going to join into the NACS standard, and this enables them. One of the big motivating reasons for doing this is to essentially be able to take advantage of Tesla's charging network, which is by far the largest charging network in the country, and can provide accessibility for a number of other reasons. But you can see here that pretty much all major auto companies end up announcing a switch to NACS. It's not going to happen overnight. A lot of the vehicles being produced are still CCS1, although there are a number of vehicles now that have, like new vehicles that come out, where you're actually using the default plug is the J3400 standard, or the Tesla standard. And it wasn't until December of 2023 that SAE kind of formally announced and published their J3400 standard. Okay? Any questions about this? Okay. Yeah, and then a couple more. So let's talk about infrastructure deployment a little bit more broadly and what that has looked like over time. So the first thing is to think about kind of the biggest one is deployment of this stuff at home, right? And so, you could use the level 1 and just plug it into a wall, but a lot of people feel that that's maybe a little bit too slow. And so what you see here on the right-hand side, these are a bunch of different level 2 chargers that you could buy and use at home. There is kind of this question of, well, not everyone lives in a single family home with a detached garage that they could set this up easily, right? And so, what about if you were to live in like a duplex or a townhouse, or if you're living in an apartment building, right? The amount of support for a particular type of charging is going to differ, right? And so you can see here on the left-hand side, some apartments can do level 1 or level 2, but then a bunch of them, right, actually can't really support charging as is. You might have to upgrade or retrofit things. And then even in the single family homes, right, we do have a lot that can do level 2 and level 1, but then there still are some portions that don't have the ability to do that. And so if we think, today, the type of people who are buying electric vehicles are usually the ones who have access to charging. You're talking about large swaths of the population that don't have access. And if we're doing 80% of our charging at home, right, are people actually going to buy electric vehicles if they don't have the ability to do this? So that's an important consideration, and it's a topic and problem that a lot of folks are thinking about pretty actively right now. And then how much does it actually cost to charge at home, right? So it depends on where you live, the time that you charge. If you have solar, you can be on a specific EV rate. So, the math is maybe a lot simpler for gas, where I drive to a gas station, I can see the advertised price, and then, I can see the amount of money I'm paying when I actually pump my vehicle. Whereas for home charging, right, that's going to just show up on your electricity bill. And, unless you're paying close attention, who knows how much of that electricity bill is actually going to your car, right? So, okay, who here lives in Davis? Raise your hand. Okay, who lives in Sacramento? Anyone? Is anyone here? Yeah, okay. So, yeah, if you were to charge a car in Davis versus in Sacramento, you'd be paying like 3 times difference in the price of electricity, because in Davis we're on PG&E rates, whereas in Sacramento we're on SMUD rates, right? So imagine, right, paying $3 a gallon for gas versus $9 a gallon for gas, right? That's kind of the difference in scale that we're talking about here. Yeah, so in SMUD, you're talking about on the order of like 12 cents a kilowatt hour. That might be something like 80 cents a gallon of gas equivalent, right? Whereas in PG&E, we're probably paying more on the order of like $3 a gallon equivalent of gas, which is still cheaper, right, than what we have today, but still very different depending on where you live. And you can see the structures here. Actually, I have a different slide on this. Yeah, here. Electricity rates can get pretty complicated, right? So you have, on the left-hand side, I don't know how many people are super familiar with the way that they pay for electricity. We, by default, if you're on PG&E, you're on time of use rates, which means from certain times of the day you pay more for electricity, and certain times of the day you pay less. And then you're also on these like tiered rates. So if you use some amount in a given month, if you use under some amount, then you pay a certain rate. And if you use above a certain amount, then everything above that goes up in rate, right? So the electricity rate structures can get pretty complicated. So on the left-hand side, this is kind of classically what they show you for PG&E. Yeah, and also I should say it differs between summer season and winter season, right? So we are currently in winter season, so between October and May 31st. And if you're on your first tier, you pay 38 cents per kilowatt hour between 9 p.m. to 4 p.m. And then from 4 p.m. to 9 p.m., you pay 41 cents per kilowatt hour. Okay, this is actually definitely outdated. The updated numbers are probably more like 37 cents off peak up to like probably like 50. Oh, okay, no, that's tier 2. Yeah. So actually, this is right. We do have the current one. Yeah. So base tier 38 cents up to 41 cents. Top tier, you're 49 cents up to 52 cents, right? So much more expensive. And if you happen to live in Sacramento and you're in SMUD, there's a similar type of thing, but although they have multiple, they have what's called off-peak, mid-peak, and peak. Off-peak goes from midnight to noon, mid-peak is noon to 5, peak is 5 to 8, and then back down to mid-peak, 8 to midnight. And here it's 14 cents off-peak. Actually, if we compare non-summer, so we're doing the same thing, 11 cents off-peak compared to 38 cents, and then 16 cents on peak compared to 41 cents, right? So very different electricity rates. And so the general takeaways from this is that one, the location dependency and the timing of charging can have really big impacts on how much it costs. And two, generally speaking, the cost of charging at home is less visible to people than the cost of charging at a gas station, where you can like see that price in your face as you're fueling, right? We also have chargers at work. Companies provide workplace chargers to employees as benefits. And there's a whole sort of thing about charging etiquette that can get kind of interesting. So the cost, when we think about costs, right, depends where you work, can be free. It could be discounted compared to home, and then it could even be more expensive than charging at home. Often we have other time limits or increased fees in order to encourage people to like move their cars once they're kind of done charging. So, one example of this is, at UC Davis, right? So we have parking here, and you guys may have noticed there are chargers in and around campus, right? There's a bunch in the big parking garages. There's a bunch of chargers by the Arc, right? So technically, in some ways, charging there is quote unquote free in the sense that you don't actually pay for the electricity going into your car. And so if you like filled up from empty, you could get a pretty big benefit out of charging here at Davis. There is it's not totally free in the sense that there is a surcharge on parking. So, I don't remember what it costs to actually park in a day here anymore. But if you park and charge, you have to pay like $1 or $2 extra. But that's often worth it if you're charging enough. Right, and it doesn't take much. You'd only need to be charging for, an hour, hour and a half to break even, and then everything after that is, extra on top. Okay, we also have public charging, right? So these are the three main formats we think of. It used to be described as home, work, and public, and it gets a little bit muddy. People have debated on the sort of proper usage of saying home, work, public, but I'll just say that that's kind of the most common ways that we describe chargers is these three categories. So public chargers, unlike gas stations, right, which are these kind of standalone locations where you're just meant to kind of fill up, the nice thing about chargers is that while we often are putting them at places that are convenient for consumers, either you're going to a location that happens to have a charger and you're able to use that as an extra service, or you're going to this location specifically to charge but has these amenities nearby that you can use, right? And so like Walmart has these has agreements with Electrify America to set up networks near their stores. Target often deploys ChargePoint chargers. IKEAs will often have agreements with charging network companies. this one is now, the bottom left one is, this is Whole Foods, not the other one I was thinking of. Well, so Whole Foods used to have, I don't know if it's still happening, but they used to have agreements with EVgo. Yeah, and so lots of different formats of these chargers, and they are deployed kind of strategically in ways that, you know, you might have level 2 at places where you're going to spend more time, right, like a movie theater, and then you might have DC fast charging in places you might only spend, you know, 20 to 30 minutes, like near restaurants. There often is a premium associated with charging at faster charger locations. Tesla, this one is a little bit outdated. I would probably scale this up by double, probably at this point. And then Electrify America, right? Here you're paying 56 cents. This is in Davis. And here out in Vacaville, you're paying 64 cents a kilowatt hour. So that's higher than what you would be paying at home. And that's very common for these DC fast chargers. And the idea is that you're essentially paying a slight premium for the higher speeds, okay? And so at these electricity rates, you are likely paying more on the order of like $5 a gallon of gas, right, equivalent, just to give you guys some context, right? And so fast charging is definitely gonna be more comparable to like filling up the cost at a gas station. But most people are not doing this all the time, right? You may only be doing this, you know, when you're doing long distance travel, and most of the time you're probably charging at home at cheaper rates. What does charger deployment look like in the US? Actually, you know, a lot of people think there's not that much out there. But I think that's more having to do with the visibility of these chargers. And if you're like not really looking for them, you might probably miss them a lot. But in general, we have quite a few number of chargers. So specifically in California, right, there's about 16,000 public charging station locations. They're averaging something like 3 to 4 chargers at a particular station. So in totality, something like 43,000 public charging ports. For DC fast chargers, right, so if you're thinking more like the gas station model as opposed to slower charging, we have about 2,000 station locations and about 11,000 charging ports. And that is in comparison to about 8,000 gas stations across the state. So when we do the like one-to-one comparison of like a DC fast charger acting like a gas station, yeah, there's definitely less, right? We've got 2,000 stations as opposed to 8,000 gas stations, but it's growing quickly, and proportionally, right, there's about 2 million EVs in the state of California, and there's about 30 million cars, right? So about a tenth. Whereas chargers wise is only about, that gap is smaller. It's only about a fourth compared to the gas stations.
Okay.
Yes.
How come there are more fast chargers in the remote locations?
Yeah, so
Like just because they don't want to sit out there and wait?
yeah, so let me kind of describe the way that I typically think about the deployment of fast chargers. Yeah, I guess we'll talk about this a little bit later, but the idea is I kind of break it down into 2 types of chargers. So you have chargers that are built in like a competitive environment. So this is alluding to what we were talking about before, where I see a lot of electric vehicles in a neighborhood, and I, as like a charging service provider, I'm like, oh, there's an opportunity for me to make money. Let me put a charger there. And so I think of this as chargers in more urban locations where you have higher density of electric vehicles that are using my charger enough that I could actually be making money. That's kind of one class of chargers. The other would be, what about chargers that don't get used very often, but we want for accessibility reasons? Because I want to be able to go from point A to point B without having to worry that there's no chargers available. Those ones will be underutilized, and so from a financial perspective, not very competitive. And so as a service provider, I'm going to be like, well, I don't really want to put a charger out there and lose a bunch of money. So what you see on this map, there's a much higher density of chargers in these urban areas. So I'm thinking like Bay Area, right, Los Angeles, and yeah, even San Diego to some extent. Those are in that first class of chargers. And then the non-competitive chargers, this is all about accessibility. This is like, I want to drive from LA up to Davis, and so I'm going to take, the I-5 or the 99, and I want there to be chargers there. They're not going to be as heavily utilized. So those ones are often the ones that are relying more on public funds or that the government is helping to deploy. So we do see chargers kind of spread out along the highway network, and I would describe that as really having to do with accessibility, making sure that I have a network that I can go anywhere that I want. And then the real high density of chargers is in the urban areas, right? So in the Bay Area, Sacramento, LA, that's where you see a much higher concentration of dots. Does that answer your question? Great. There are a bunch of different brands. I've listed here maybe some of the most prominent ones. You got ChargePoint, Electrify America, EVgo, and then Tesla. And you can see purple is Tesla. They have kind of the most dots and the largest dots, right? They have the most ports at any given location. I don't know if you guys notice, right? If you drive by and you see charging stations, usually if you're driving by like an Electrify America or an EVgo, you're gonna see like 4 to 8 chargers. If you drive by a Tesla one, you could be seeing 20, 40, 60 chargers. And they have, right, a different system. They have thought about their deployment in a very different way. Whereas EVgo and Electrify America are really about thinking about the charger ecosystem as the kind of business model. Tesla thinks about their chargers as loss leaders. They put out way more chargers and they lose money on that in order to get more people to buy Teslas, right? So that's something, in the investment world we call like a loss leader, where you put an investment into something, you're not necessarily expecting to make money off of it, but you get bigger returns from other products in the future. Electrify America, EVgo, and Tesla, they all own and operate their own charging networks, but that's not the only business model. ChargePoint, for example, that you see here is another very common charging service provider. They do not own, they basically sell their services and equipment to third parties. And so if I'm Target, right, down over here in Davis, I buy some ChargePoint chargers and I install them, and then ChargePoint will service them and maintain them for me, and I can use their kind of network and system. But I would be responsible for, purchase and upkeep and the cost of the equipment. So different business models depending on the brand. Yeah, Justin Davis, right? These are the public chargers. We have a bunch of level 2 in green. These are all the locations on campus. And then in orange are the DC fast chargers. So there's the one by the Safeway on South Side. Over here, there's a bunch of Tesla chargers. And then you've got the EVgo behind, I guess, what used to be Whole Foods in the Davis Commons. And then there's another, I guess that one's over here. Then there's Electrify America in the Bank of America parking lot. Yeah, so just to give a sense and context, when we break down by brands, so total number of locations, ChargePoint and Tesla are far and away the most, followed by EVgo, Electrify America. These are kind of your top 4 brands. And then in terms of total number of ports, Tesla far and away, wins that battle. Their stations are the largest by far, and they have a larger number of stations than most other brands. Okay, any questions? All right, let's move on. Reliability. Okay, so this is a really big topic in the charging infrastructure world. There was, I think this really was kicked off by a Berkeley study that was published in like 2021 or 2022. They basically sent a bunch of electric vehicles around the Bay Area and tried to charge them at a bunch of different locations, and they found something like over a third of them were inoperable for one reason or another. And so that kicked off a huge debate in the regulatory community. So government was looking into it. Automakers were also, it's bad press for EVs. So they were kind of looking into this as well, and alongside the charging service providers. So gas pumps. Over 100 years of development, there's very few major companies, you have standardized equipment, everything's really kind of mature, and it's very profitable, right? And so you have definitely a big motivation to maintain the reliability of this stuff. And so you don't really hear about too much issues with reliability when it comes to gas pumps. But the same can't really be said for chargers. So in the early 2020s, right, there were all these popular press and media about the reliability of chargers. So I kind of wanted to pose this question to you guys, what does it actually mean for a charger to be reliable? So let's do our kind of last quick discussion. We'll spend just a couple minutes here and think about, what you guys think reliability means for in the context of chargers. Okay, let's reconvene. All right, what do you guys think?
Charging reliability is kind of like depending on the night, and we expect it, maybe not 100%, but we expect it to be within a margin of error, like it charged the way you should use it.
Okay.
And that's like reliability is kind of if you get something like if you like start up your car and then all of a sudden it's like, oh, that didn't fully, work.
Yeah.
Might be a little concerned around that. And then one thing that I brought up was like when you're waiting for gas, you kind of in your brain know, okay, I'm like about 10 minutes away to filling up.
Uh-huh.
But with this, like people will just park there, go to the grocery store and kind of do whatever. And so there's not as much reliability of when do I get to use this charger and like
Okay.
that way.
Okay, so access as well.
Yeah.
Yeah. Okay, what about you guys over here? What do you guys think?
I think it should be something that you have access to, and something that doesn't take like 8 hours to get you like during class or
Okay, so so speed matters to you. Okay. Anything else you guys talked about? Reliability.
Like compatibility with your specific vehicle.
Okay, you want to generally, yeah, and this would tie to the accessibility piece. You basically, I don't want to deal with all these standards, just like let me plug in my car and charge it, right? Okay? What about you guys over here?
It's just like from a consumer perspective, reliability is just like your ability to show up and plug it in and get the power that you're expecting to get.
Yeah, that's great. Did you?
Pretty much just like
Yeah. I don't want to have to think about all these different issues, right? I just want it to work. That's an important point. I think I'm about to talk about all this like technical stuff about reliability that all the different stakeholders are thinking about, but there's actually often a disconnect between like all the like standards and requirements and reliability that a car company or a charging network might be thinking about, and how that relates to the reliability that a consumer wants, right? Those things may not necessarily be the same. Okay, and we're going to see how that plays out in this context. Okay, so with all of this negative press on how reliable chargers are and the problems that people are having, government decides to step in. So back in 2021, so this during the Biden administration, they passed the bipartisan infrastructure law. Part of that law established this National Electric Vehicle Infrastructure Program. I don't know if anyone's ever heard of this. So this is also called NEVI, so NEVI. This was $5 billion to establish a charging network on the US highways across the entire country so that EVs can kind of drive and be able to charge anywhere in the country on these sort of longer distance trips. Okay. Again, going back to this concept that like government can often step in to provide more public service or public good type services, right? And so we think having a national network that allows for EV technology to be enabled, yeah, that's something that the government or that we as a society want, and therefore the government supports. So they formed, actually for the first time in US history, outside of the military, a joint office between multiple regulatory agencies. So this is between the Department of Energy and the Department of Transportation, right? So it's a really nice cooperation in the sense that the DOE is very familiar with like the technologies, and DOT is really familiar with implementing these large financial programs having to do with infrastructure, right? They install like national highway systems, right? And so combining forces here to essentially help implement NEVI. Okay, what does any of this have to do with reliability? Well, actually, part of the rules for the NEVI program was that, okay, if you want to take government money, you can't just install these chargers and run away, right? Actually, which was a specific nod to an earlier program that was implemented in the earlier 2010s where the federal government gave a bunch of money and people would just install chargers, take the money, and then leave the chargers to rot, and they weren't maintained. A lot of them were like really poor equipment and all of that. So here, government said, if you take our money, you have to follow a bunch of rules, okay? So part of that requirement is this idea that you would have minimum uptime, right? So that the chargers have to be up and running and working like 97% of the time. So a charging port is considered up when its hardware and software are both online and available for use. And then they have this specific equation to like calculate. You don't need to write the equation down or memorize it or anything. This is just what was actually written in the regulation. Yeah, and so this is like a good, I think, step forward, right? The idea is that I don't want to drive up to a charger and see that it's like offline and not working. The intent here really is to address this idea that like, oh, we've seen all these reliability issues with chargers. Okay, but going back to this idea of like, how does this actually mesh with the experience of a consumer, right? Uptime might be a good starting point, but it doesn't accommodate everything, right? So doesn't count block chargers. This is an example out in Tahoe, right? There's a embankment of snow, so some snow plows just like push a bunch of snow up against the charging charger locations. So technically available online, ready to go, but completely inaccessible, right? Doesn't count chargers getting blocked, right? So here, chargers are available, up and running. Technically, if I look at the data, uptime would be totally fine, but right, I wouldn't have access to this. Doesn't count fake availability. Okay, so this is out in the Vacaville outlets. Yeah, we took this picture, right? So here, this is Electrify America network. There's 8 chargers here, and according to the app, it says 6 out of 8 chargers available. But if I drive up here, well, doesn't really look like there's that much availability, right? It doesn't count issues when you can't start a charge, so it might be up and running. So here, this is a level 2 plug. It says, sorry, the station is charging another EV. Please try again when the station is available. But you can see the plug is just like plugged into the, yeah, it's just sitting in the nozzle, right? So there's no car charging there, even though it says that it's currently being used. Huge issues with the payment interfaces where like credit cards can't be read. Yeah, and there's a whole kind of debate about credit card readers in this world too, which I won't get into. And then like point failures, right? So charger is up and running, it's working, it's online, it's got it's got communication signal. Then I plug into the car, and then something goes wrong, right? So point failures don't really count towards uptime either. It also doesn't count throttle charging, right? So the idea that, okay, I'm at a 350 kilowatt charger, I plug in, and it's charging at 60 kilowatts instead of 350 kilowatts, right? So, imagine you're trying to fill up your gas car, and you're trying to fill it up, and then it starts dispensing like a couple drops at a time, right? That's essentially what throttle charging is it's much lower than the actual power rate. So actually, over the last couple of years, there's our EV Research Center here at Davis has been involved in a study with the state of California to try and understand what the failure rates actually look like. So we actually had, we sent students out to chargers all over the state to try and measure this. And so these are some of the results that we're seeing from that. And so how to read this is essentially these are all of the tests, these are all the ports that we looked at and were able to test. And everything in the top is successes directly from plugging in. And then we also make observations on how other vehicles are doing. And that's this kind of piece here. And so some of them are successful, some of them weren't working, right? And we tried to do, I think the whole idea behind this particular project was to understand more on the consumer experience side. And so where were we seeing things like credit card failures happening, when charge interruptions were happening? How often were we seeing issues with like navigation to the charger or congestion at the charger if there's like long lines, or if the chargers themselves were like blocked, right? And so anywhere we are observing these failure rates, right, at the consumer level of between like 10 to 30% for DC fast charging and between like 7 to 17% for level 2. Okay, any questions about that? Yeah.
I don't know if you know, but I was just curious what, if you know the confidence interval on that?
Yeah, so that depends on the way that we would ask the particular metric, and I wouldn't know it kind of off the top of my head, but generally speaking, you know, we would think about, you know, the idea that we would want 97+% uptime to be reflected as kind of the charger experience. That's like very clearly not happening here, right? You know, whether it's 1 in 10 or 1 in 3 times you're seeing a failure, not great. And so this may ultimately end up translating to like recommendations or regulations to help fix this, but this is kind of the first step in at least quantifying the issues here. And I'll also say, right, this is, you know, I'm not totally blaming automakers or charging service providers here, right? It's a difficult problem, particularly because reliability isn't just like one thing that you're fixing. It's all of these things that we've been talking about, right? And so, okay, for availability, maybe they can do a better job with sensing and fixing the app, right? But like, it's not, we wouldn't necessarily say it's their responsibility to make sure that, you know, the snow is plowed and that other people aren't blocking it, right? Maybe that's more on the site host or the manager of the parking lot, right? And so you have a lot of different stakeholders needed to improve these charging experiences. What we are trying to do here is, I think there's been a lot of focus on the interoperability and the standards, right? So a lot of automakers saw this reliability problem. They're like, okay, I need to focus on fixing the standards. Whereas like, okay, that's, you know, that is these failures here, right? That's like a small piece. But then all of this other stuff here, these are all issues that wouldn't be addressed by that. And so we want to provide like a bigger picture to stakeholders that it's not just like one thing that needs to be fixed. Okay. Congestion, that's kind of an interesting one, right? So congestion is the idea that like, oh, there's a bunch of vehicles at the charger, and so when I go and I want to, you know, charge, I have to wait, you know, or I have to go somewhere else to charge. Right, so is that a reliability issue, or is that, you know, or not, right? And on the one hand, congestion is kind of a good thing for the service provider. It means people are using my station and I'm making money, right? And so we, in some ways, like that because the sort of financial picture for these guys is more positive. On the other hand, you know, if you want to solve this problem and you say, let's build out more chargers so that when people arrive, they don't have to wait, right? That means you have a bunch of chargers that are sitting around empty all the time, and so they're underutilized and not making money. So there's this kind of balance that people are still trying to figure out about, how much of an issue is demand congestion at chargers. And the other thing is like, how am I sizing it, right? Am I sizing to handle the total peak, or am I sizing it to handle kind of the average, utilization, right? So the kind of famous example of this is for Thanksgiving holiday. You have a lot of people driving from Northern California down to Southern California and vice versa, right? So any of you guys who are from LA or San Diego over the holidays, maybe you drive down to spend time with your family. And likewise, there's probably a bunch of people in UCLA or Irvine driving up to the Bay, right? And so you have a lot more vehicles at like specific times of the year. And so there are chargers along Highway 5, halfway between, that have a huge number of chargers that almost never get used, but then on Thanksgiving week are completely full, like 24/7, right? And so how do we size these things correctly? It's a fundamentally difficult issue. So more chargers isn't always the solution to congestion. That could actually lead to more inefficiencies. Okay, so because of this problem, actually, during the time, like a year or two after NEVI came out, a bunch of stakeholders came together to establish this National Charging Experience Consortium called ChargeX. And their whole mission is to improve consumer charging experience by improving reliability and other issues related to the charging experience. So this was a conglomerate of national labs, but then includes a whole consortium of different members, including charge providers, automakers, infrastructure manufacturers, other consumer organizations, and then like academics like us. So there have been a couple of working groups that help to figure out what the charging experience is, how to triage charging reliability, and then what solutions can be developed. And so if you're interested in this area, there are some great reports that have been published out of this consortium over the last couple of years. Okay, any questions? Okay. So, okay, all right. I think that there's maybe too much material to cover by the end of class. So what I'm going to say is we will cover the rest of this material next class, and we'll end just a little bit early. And so we'll do infrastructure costs next week on Monday. Thanks all, and remember that the first homeworks are due today by the end of the day. So make sure to get that in. Otherwise, I will see you guys next week.